Welcome to my YouTube channel. I am Dr. Prabharan. In this session, we are going to discuss about molecular rearrangement. Rearrangement is referred to the migration of an atom or a group of atoms from one atom to another within a molecule or from one molecule to another molecule. There are two types of rearrangements. One is intramolecular process, another one is intermolecular process. The intramolecular process, the migration does not become completely detached from the system, whereas intermolecular process migrates group first detached and later reattached to the another site. Basically, this is elimination addition reaction. There are the rearrangements reactions are classified according to the nature of the group which migrates. For example, the rearrangement to electron deficient carbon, the rearrangement to electron deficient nitrogen, rearrangement to electron deficient oxygen, rearrangement to electron rich carbon, and also aromatic rearrangements. There are different classification. Each classification have different methods. For example, the rearrangement to electron deficient carbon, we are going to discuss Wagner Meerwein rearrangement, phenol rearrangement, benzylic acid rearrangement. In the case of rearrangement to electron deficient nitrogen, so there are 5 different methods. One is Hoffman rearrangement, Curtis rearrangement, Schmidt rearrangement, Lawson rearrangement, and Beckman rearrangement. And for another one is rearrangement to electron deficient oxygen. That is, we are going to discuss Dyer-Villiger oxidation and Deakin reaction. Another one is rearrangement to electron rich carbon. There are 3 methods: Units rearrangement, Wittig rearrangement, and Pavlovsky rearrangement. And also we are going to discuss aromatic rearrangements. We have discussed molecular rearrangement and their types and classification. Now the first example of rearrangement to electron deficient carbon, the Wagner Meerwein rearrangement. The rearrangement involving the change in the carbon skeleton through the rearrangement of carbocation as intermediate. In this rearrangement, the carbon migrates with its bond pair to an electron deficient atom. For example, alkyl halide in the presence of acid gives the mixture of product. So let's have a look mechanism. So in the presence of acid, the primary carbocation is formed. The primary carbocation is less stable compared to tertiary carbocation. So the 1,2-methyl shift. So primary, now we'll get a tertiary carbocation. Tertiary carbocation is more stable than the first carbocation. Now the elimination of hydrogen gives the product, the O-ethyl. We'll get 2 different products. There are different ways to generate the carbocation. First, from halide. So using strongly ionizing solvent or by adding a Lewis acid such as silver ion, which leads to carbocation formation. For example, Cl, alkyl chloride, gives the formation of primary carbocation. The second method is from an alcohol. So if you take alkyl alcohol in the presence of acid, the oxonium ion will go out, you will get a primary carbocation. So the third method is from an amine. So if you take amine in the presence of nitrous acid, HNO2, you will get a primary carbocation. Fourth method is from an alkene. So if you take alkene, if you react with acid, you will get a secondary carbocation. Primary cation is less stable compared to secondary cation, that's why it's forming the secondary carbocation. So the next method is hydrogen migration. So if you take this, so it leads to hydrogen migration, you will get a tertiary carbocation. The next one is the formation of phenonium ion. So if you take this example, so this phenyl assists to eliminate this chlorine, so you will get a phenonium ion. This is highly stable. In this, one more important thing is electron releasing group in the aromatic ring gives rise to greater rates of migration, whereas electron attracting group lower the migration rates. Let's discuss some more example from Wagner Meerwein rearrangements. In this case, the decanol in the presence of acid forms the oxonium ion. Next step, the elimination of water. So at the same time, we will get the migration of carbon. So we will get a tertiary carbocation. Then elimination of hydrogen gives the alkene product. So if you look at the second example, the same way, so formation of oxonium ion, OH2 methyl. So oxonium ion eliminates water molecule. At the same time, migration of methyl group. So H methyl plus elimination of hydrogen will give the alkene product. So let's have this one the same way. This forms the oxonium ion. So this eliminates, this methyl group migrates to here. So basically this 4-member ring extended to 5-member ring. This is above the plane, the formation of secondary carbocation. This is methyl, this is methyl. So further which attacks to the carbocation, so gives the ring expanded product. Let's discuss previous year question paper. In the first question, what is the major product? We already discussed this phenyl forms the phenonium ion which is stable. So once this tosyl groups leaves, so it forms the formation of phenonium ion. Then the acetate attacks below the plane, so gives the product of acetate, methyl, hydrogen, methyl, and phenyl. So the answer is A. So let's have a look this one in the presence of silver nitrate. So elimination of bromine. So ring expansion happens. So what happens? This bond comes here, so leads to 6-membered ring. So double bond Br. So the position here is positive, H2O. Forms the OH. So the correct product is the B. The third example is the formation of oxonium ion. Tertiary carbocation, the hydrogen elimination gives the alkene product. So also, so hydrogen can eliminate here. So this will give the product of this. But if you compare this and this, the more substituted alkenes are most stable. So the correct answer is C. So if you look at this example, so what is the product? So elimination of chlorine, the methyl shift. So what you will get is here plus methyl. So if you chlorine, so you will attack here. So what is the product? Cn. So but in this it's the given rearranged. So start writing the numbering 1, 2, 3, 4, 5. Okay, this is 6, this is 7. So if you write rearrange structure, so here is the chlorine. So 1, 2, 3, 4 and 5, 6 and 7. If you see this bridge, 5 and 6 and 3 and 7. So this is a exo product. So I am giving here 3 problems to solve in your home. Try to solve it. If you like this video, share with your friends. Thank you.